yeah, today we're going to be talking about kind of accelerating battery cell innovation with conductive coatings. Um, Kind of the layout for how I position this talk is we're going to start with just a general understanding what these kind of core properties of conductive coatings are and their advantages. Move into some use cases as to when it kind of makes the most sense and how we maximize the impact from these materials. And then we'll get into kind of the Henkel specifics, advantages of our BCC technology. So that stands for our battery conductive coatings, which is kind of what we refer to these materials that are mentioned before. Michael said a buffer coating or primer coating, some other terms that you might have heard used before. I'll also touch on our Henkel capabilities, kind of end with some of my personal perspective on future directions in this area. So, kind of what are conductive coatings? At the core, they're dispersions of carbons in polymers that get applied to typically metal foils. So, here's showing aluminum. This would be a cathode. Um, and if you look, it looks like just a smooth black paint on the surface for these really thin coatings. But as we kind of take the technical approach to look at the surface, here's showing an AFM image. The surface is actually not so smooth. It imparts a bit of surface roughness. Um, so these coatings kind of change what that current collector surface looks like that the active materials then see in the fabrication of electrodes. And with that, the conductive coating. So they're designed to increase the surface area and roughness. It allows for some stronger adhesion between active materials and current collector foils. We'll kind of talk about the resulting impacts of this relationship. So as you look, if you kind of peel back the layers, we're taking this electrode. I'll use that just not referring in particular to cathodes or anodes, as these materials can be used on both sides, but kind of turning it into a slightly more layered structure, kind of with our conductive coating in the middle of the sandwich, where we're adhering to the underlying current collector and also that of the active material. So it's very important for us to adhere strongly to both of these materials and have the appropriate interface formed with both materials to facilitate improved electron transport across that of the electrode. So I say that we kind of get into these buckets of where we see areas of improvement when using these conductive coatings. And we'll walk through it today, but it does depend on how you're manufacturing electrodes and materials being used as to where that kind of core advantage comes from. And there's also not kind of a one size fits all conductive coatings. It's important to kind of design this interlayer material appropriately for the use case. So our three buckets are largely physical adhesion, electrical conductivity enhancement, and then some anti-corrosion electrochemical protection that it provides, just purely as a more barrier coating there. So when we look at kind of the schematic to kind of take that previous cartoon that was replaying there and look at the cross section of this layered electrode structure, we have our active materials here, the current collector, and as I said, sitting in between is this conductive coating. Now, these coatings are typically very thin. You'll never really see them much more than 2 or 3 microns. Typically, the state of the art is pushing to 1 micron or even lower yet. So these are really thin comparatively to current collectors and especially to that of the active materials where they might be tens, even hundreds of microns thick. So with that, it sort of brings me to kind of understanding some of the main use cases of conductive coatings. Um, so this little matrix, we'll kind of talk through it, and then I'll highlight a couple of them too. But the advantages that conductive coatings brings is dependent on the materials being used and the manufacturing process that's being done. So when we look at low voltage cathodes, something like a LFP, maybe done traditionally with NMP slurry application, what the conductive coatings do here is it certainly improves adhesion, the overall structural integrity of an electrode, but you're really getting an enhancement of improved electron transport across this electrode. It really enhances the overall conductivity, gets rid of some points of high resistance that are typically found within LFP cathodes. As we move towards high voltage, something maybe like your NMC cathodes, again, via an NMP slurry-based process, It kind of reshapes the way we think about this when using a conductive coating, in that it doesn't necessarily provide the exact same conductivity benefits directly that we see with something like LFP, but what it does do, due to the enhanced adhesion and ability to maintain a high structural integrity of the electrode, is allow for some lower binder content in the active material. So it allows the cell makers to kind of rethink um, some of the materials on their side, and also provide some of the corrosion protection at those higher voltages. That is one of the areas that we'll kind of dive a little bit deeper into today. Thirdly, the dry electrode manufacturing. So this is now, instead of looking at kind of the active material case, taking the step back to how electrodes are manufactured. And with dry electrode manufacturing, not sure the level of familiarity of everybody on the call, but this is getting rid of NMP solvents, more of a lamination of freestanding films. And here, as we'll go through as well, a conductive coating kind of changes from purely a coating to actually acting as an adhesive, that allows for the lamination of these freestanding films to current collectors. Really enables this technology. Kind of last one that I won't touch much on today. There's some benefit in the high silicon anode cases, stemming from the advanced adhesion of better able to maintain adhesion between current collectors and active materials under large volume changes. So as I kind of alluded to, these are the two that we're going to dive a little bit deeper into in the next 5 or 10 minutes here. So before I get this, does anybody have any, I'm going to want to pause first here. Does anybody have any questions on those first couple slides? Do we feel like there's a decent understanding of kind of what materials these are and what properties we're looking for from them? Feel free to speak up or raise your hand. I'm also trying to monitor the chat as well, if you prefer to put there. Yeah,
Yes, please.
yeah.
Uh, the conductive coating, particularly, you talk about, would you mind to elaborate about the combination of like single wall carbon nanotube or carbon black or graphene? Those kind of additive having a different functionality, different role to play. Would you be able to elaborate about the conductive materials, what you use, for example?
Yeah, I can't share the specifics, but I'll certainly elaborate on what of those conductive materials are. So
Yeah,
we certainly use conductive carbon materials. There are use cases and advantages to using some of the more nanomaterials, whether that be carbon nanotubes,
yeah,
graphene,
yeah,
or your more traditional graphites, carbon blacks, and so forth.
yeah.
But in the end, what we're trying to do is form, well, maybe I'll just back up just a couple slides to in the end, we want to form a highly conductive network both
Okay.
within this material and then also through it, right? Because we're trying to funnel the electron transport from active materials to current collectors. So we need good conductivity in both kind of the X, Y, and the Z direction.
Yes.
So there's certainly strategies to doing that, in making use of kind of all of those carbon materials that we have available to us, to form that best network possible.
Great. Thank you.
Yep. Anything else? Okay. As I said at the start, feel free to interrupt me. I can stop this at any time and get back to it. So that was kind of just that initial background, kind of points 1 and 2 on my initial presentation overview. We're going to get into more of the 3 and 4 here. Um, So what I'm showing you here is kind of a product breakdown of Henkel battery conductive coatings. I want to show this before we actually get into some of the more specific use cases and data, just so you can kind of have the right framing of the conversation into what are some of the Henkel specific things I'm talking about. So we actually separate out from the top based on how electrodes are manufactured. And I'll kind of walk through this here on this slide. So we have our BCC 1000 series materials that is designed for this DBE type processing. So this is where that coating is both acting as a coating and as an adhesive, um, really enabling the lamination of dry films to current collectors. When we go to our 2000 series materials, different sort of requirements and properties when we're looking at say a slot die coating, a liquid-based deposition or slurry-based deposition onto our material, we no longer have to have the sort of lamination behavior, more of a traditional coating in a sense here. So while these materials look the same on foils, you wouldn't be able to tell the difference whether it's a 1000 or a 2000 series. Their functionalities, the way they're made to work within the manufacturing process is quite a bit different. You'll see many of the properties are actually pretty similar. All of our products are aqueous based, viscosities in the 100 centipoise range, a little bit different than typical solid contents. But then you get to the resin characteristics where we start to see kind of the first distinguishing difference here, where we have a very more flexible, malleable to do the lamination behavior in our 1000 series materials. And when we go to 2000, this is more of a rigid, more of a traditional barrier coating that also it aids in adhering to those liquid slurries, but really is highly solvent resistant in more of a traditional coating in sense. Why some of the properties look similar is because they're both designed to be applied in the same way. So high-speed printing processes, typically direct and reverse gravure is the recommended methods. Electrode application, you can see there. The main thing I'll highlight there is with our 1000 series materials, as it's a true enabler for this dry manufacturing technology, we really try to have our materials adhere well and be electrochemically stable in both low high voltage environments. So for use on anodes and cathodes. So we're adhering well to copper and aluminum, also maintaining electrochemical stability there. So you can kind of look at the bottom portion there of being electrochemically stable across that whole window. Coating thickness, as I had mentioned to, adhesion to the underlying current collectors is strong. You can see some resistivity, contact resistance sort of values, just the inherent electrical conductivity properties of these types of materials. And then the other distinguishing characteristic is that electrolyte and NMP resistance. For the traditional manufacturing process, that is of the utmost importance. So you see that it has extremely high resistance to NMP, also electrolytes. When we go to lamination behavior, we don't even test for NMP because it's never subject to that material. However, electrolyte resistance is still equally as important. It becomes more challenging when you're trying to have something with more of an adhesive character to it. But we certainly want to maintain an electrolyte stability and have minimal swelling kind of once the material is actually in function inside of the cells. And I show these containers down here because what we typically do is our business model or strategy is to supply these materials as the aqueous product. So we'll supply that to customers that can then coat it themselves, or if they need help coating, we'll touch on the end. We do have our own in-house kind of pilot capabilities to aid in expedited innovation specific to customers and also for initial sampling and validation. And we also work with other people across the globe in terms of aiding customers that maybe need to be put in contact with converters or people that will actually get this onto a current collector for them. Okay, so now we're going to kind of dive into those two use cases, talk about the sort of product properties that we need and enhancements that we see. So again, not sure everybody's level of familiarity, but traditional electrode manufacturing kind of follows this process of a wet mixing, a slide die coating before drying, calendaring, and eventually slitting. You can see the details on the slide there as to kind of what's happening at each step. And typically people have done this with actually out conductive coating. So it's not a necessity to be able to make lithium ion batteries. I'll kind of show you, make an argument of why it can be advantageous to look at them. So when we look at this, once we get our materials inside of a cell, it doesn't necessarily matter how the electrode was manufactured, right? We need it to maintain stability against electrolytes. It needs to have good conductivity across that full electrode, maintain adhesion across the life cycle of a battery. All of these things are sort of ubiquitous kind of once it gets inside of the cell. Where a lot of our core material design comes from is where you sort of getting it to that point. As these current collectors show up with our coating, how are they used throughout this manufacturing process? So when we look at this one, we can see that there's a few key requirements needed for conductive coatings here. We're certainly going to want to increase the surface area, provide some of that surface roughness to have better adhesion across the interface. But we also need to have that excellent resistant to whatever that carrier solvent is. On the 2000 series, it's largely cathode based, which is for NMP, but you could also have a water based system on the anode, perhaps, where you need to have strong resistance to whatever that carrier solvent is. It needs to withstand high temperatures depending on that solvent. So in the case of NMP, something like 200 degrees Celsius or so, as those materials or solvents are removed, our conductive coating needs to be able to kind of withstand those conditions because we don't want it to have any sort of degradation, and we want to have an expected performance once it's actually put inside of a cell. So when we look at this, the wet processing, this kind of just walks us through. We have the increased surface roughness from this conductive coating. And then as that active material slurry is deposited, there's kind of this natural filling of that increased surface area space to start to form this interface that we want that is well adhered and helps facilitate electron transport. This interface further gets modified during that drying and calendaring step, where these materials kind of get forced together within that increased surface area. And we see enhanced adhesion when using when using conductive coatings as compared to bare foils. And now I'll forward you. The next slide has some of the data. There'll be a little kind of a lot to work through. So if you have any questions along the way, feel free to stop me. So this is where we actually get into, okay, when we compare to bare foil, what is the advantage of using a conductive coating? And my main take-home message on this slide as we get through it is kind of to see the most significant impact. We need to really understand the manufacturing of the electrodes and the materials that are being used so we can best design and recommend a conductive coating to elicit the highest level of impact on the cell, highest level of performance improvement. So here I actually show a 2000 series material and a 1000 series material through some coin cell validation testing. And what we did is just do the traditional manufacturing setup of a kind of literature NMC 532 active material. So in this case, the 2000 series material of ours is designed exactly for this type of system, this type of manufacturing process and materials being used. The 1000 series material is not, right? This is something we would not recommend to use with an NMP slurry process, and you'll kind of see why. So you see some coin cell particulars, but I'll take you to the bottom right here of some of the results and analysis. So you see when we actually design the material for that manufacturing process and the materials being used, we start to see a pretty significant impact. Capacity compared to bare foil after 100 cycles, nearly 3%. It kind of maintains this across the life of the battery for a life cycle improvement over 18%. If we use a material that sort of looks the same on the foil but has different underlying properties, you do see some benefit, right? There is a little bit of benefit here. We do see some increase in initial capacity that furthers the life cycle improvement. But to add manufacturing steps and potential cost inside of the cell, this might not be good enough for the cell maker. So the point here is to kind of iterate that it's not a one size fit all. You can't use a conductive coating, just treat it as a carbon coated foil and expect it to work in your system based on how you're manufacturing and the materials that you're being used. Okay, I'm going to switch gears into the second use case for dry electrode manufacturing. Any questions on that first part? Otherwise, I'll keep it going. Feel free to use the chat as well. Okay, just double checking. Nothing in the chat yet. Okay, so when we get into dry electrode manufacturing, this might be something that's a little newer for people. It hasn't been around for quite as long, but the core difference is in that first part of the electrode manufacturing process. Instead of a slot die slurry based coating, it's a dry mixing of powders, usually some sort of freestanding film formation or perhaps a spray of those materials. And then it goes through a lamination and slitting behavior. So, when we start thinking of what properties we need from conductive coatings here, this is where we go from that traditional just coating standpoint to something that's now also acting as an adhesive that can adhere to these freestanding films under the necessary temperatures and pressures that are typically needed for different binder activations and to avoid damaging active particles. So why do we need this? And I said before, it's a technology enabler, and this sort of slide summarizes that. So if you just try to adhere these freestanding films to current collectors, they don't really adhere much at all. You can use high temperatures and pressures, and they're not going to stick. You get pretty high resistance rise, capacity fading, and overall processing issues of just the material fully delaminating from itself. So you really need some sort of adhesive layer that is also highly conductive there, that has sort of full coverage like a coating would, um, to kind of get the optimal interface. The reason that these typically don't stick, a lot of these freestanding films are uh, just consist of active materials, carbon additives, and very small amounts of fibrillized binders, typically fluorinated ones like a PTFE. So in contrast to a wet processing where there's kind of this natural interface formation due to the liquid kind of penetrating the surface roughness, um, these freestanding films kind of don't have that ability. So it requires some sort of modification to help enable this technology. One of which is these conductive coatings to kind of modify that current collector or foil surface. So again, kind of walk through the importance of the material selection and understanding of a process from a conductive coating standpoint. So here I'm going to introduce you to two terms, a passive and active conductive coating system. So this passive conductive coating system is kind of what we just talked about. More of a rigid, true coating, no real lamination behavior, just a kind of enhanced surface roughness. When we try to put the dry film on that, we can use all kinds of heat and pressure and we force the dry film to adapt to that conductive coating. What ends up happening is you kind of get point adhesive contacts. You don't get this nice blended interface. So what Henkel has done is develop what we'll call this active coating system, where this coating now starts to behave truly like an adhesive. So what happens here is when we go do this film application, this dry film, our material is actually going to adopt with that dry film. So this allows kind of almost a wetting of the surface of that dry film to kind of really increase that bond strength at that interface and therefore enhance our conductivity. We can actually see this under a microscope after lamination, where if we use a passive coating system or a reference that's out there, um, you'll see this very kind of defined interface between the conductive coating system and that of the active material. There's often a lot of void spaces near that point where there's not kind of full contact across that. When we go to our active system, you'll see that this interface gets a little more blended. We typically don't see voids at this interface, and we get a really strong adhesive performance between the conductive coating and these dry films. So when we take this kind of the next step for the technical validation, Henkel, we don't do DB type processing. So we worked with a research institute to do some of these studies here. You can see kind of the dry electrode formulation up there in the upper right. And we're going to be comparing kind of our 1000 series, this active primer concept to that of a passive primer concept reference material under different temperatures and pressures and looking at adhesive strength and how conductivity is impacted. So when we do this, you'll notice that if you push really high temperatures and high pressures, you can kind of get them to adhere similarly. You'll see on the next slide that the conductivity is still not quite as good, though. But where we really get the advantage is we start adhering even at room temperature with these materials, as long as adequate pressure is there. Typically, we would target something in this range, maybe 110 degrees Celsius is where this material is going to have that best lamination performance to really enable dry battery technology. So a couple key points here. That the part that's kind of not captured here is those red bars are all cohesive failures. So that's what we target in terms of our adhesive strength in this system. Typically, those freestanding films are not all that cohesively strong themselves. So we always want the failure mode of being those active materials to just be ripped in half. We want to maintain adhesion to the foil and that active material and allow that failure mode to be that cohesive failure of the active material. And that's kind of the maximum level of adhesion that we're able to get. So across all of those temperature ranges, we're seeing that. You do see some change as those conditions do impact kind of that cohesive strength of those films themselves. So this active kind of system enables this technology, allows for milder processing condition and improved cell performance. This was what I alluded to in terms of the conductivity. So as you form a better interface, adhere, enhance the adhesion to the active material, you also see a reduction in this resistance value. So these red bars being a bit lower than the gray ones. As you're increasing pressure, it kind of maintains that same percentage improvement there. Any questions there as we take the last few minutes? I'll kind of switch gears into some of our capabilities and kind of my personal perspective on future outlooks.
Yeah, Jacob, I've got a quick question. This is Mike Rugula from Burla Carbon.
Hi there.
Uh, the and maybe this is already explained, but the at least the carbons used in your wet and the dry coating materials that you just showed, have you played around much with like surface area or different type? Do you need the same type of carbon in the wet versus the dry coating? Is that something you played around with much at all? Um, yeah.
Yes, good question. And I would say at its core, yes, it's similar in terms of the types of carbon. There's a little bit difference though in terms of the amounts, I would say. When we start thinking of forming that conductive network in that DBE processing style where we're also functioning as an adhesive, it kind of requires um, different amounts of those non-conductive materials to be present in there. So it makes that formation of the conductive network a little bit more challenging. When you go to something like the 2000 series, forming that conductive network becomes a little bit more easy. You can get away with kind of higher loadings in that case. So I would say that's sort of the challenge. The materials themselves are pretty similar in terms of what you would use, but you might need some other tools in cases to form that conductive network at different loading levels.
Sure. I probably have several more questions for you, but I'll let some other people jump in and maybe we can talk afterwards.
Yeah,
I
yeah, I do have some time after 1 o'clock too. I know they told me that it can kind of be there's no hard end here, so I'm happy to have conversations with folks beyond the time. But feel
Great.
free to drop off time permitting.
Yeah. Thank you.
Yeah. Anything else, or you want I can finish? I don't know. There's maybe 6 slides left or so. They'll go quick.
yes, continue. We can have it later. Yeah.
Okay. Yeah, so now I'm just going to get into kind of our center of excellence application capabilities, what it looks like. I said before, we typically supply materials kind of in the pails, drums, totes, but that's not always usable to the cell makers. Um, we do have a full suite formulation analytical teams on site in our R&D center for this material just outside of Detroit, Michigan, where we do all of the development. We also have our own in-house some cell manufacturing testing capabilities. And then I have a separate slide next to kind of highlight that application. So while all of the development happens uh, here in North America, we do manufacture these materials in all three major global regions. So when we look at our application capabilities, we do have a pilot coder. I mentioned before, it's designed for high-speed gravure printing processes. We're able to do both direct and reverse um, coating on this machine. We have precise tension control for thin foils, so coating something as thin as 6 micron electron deposited copper to 10, 11 micron aluminum. Independent oven zones. We can get to 50 meters per minute on this machine. That's a little lower than kind of typical manufacturing processes, but it's getting close to what some smaller converters and stuff might use. One of our main constraints is terms of foil widths and foil lengths, so you can see that. But this is hugely valuable to us from an R&D effort to ensure that our materials are high quality and able to be high speed applied, but also an advantage for the customers and people we work with. You don't have to necessarily have the equipment in house to be able to do this, and you don't have to find a converting partner for at least those initial lab scale sort of developments and validation. I talked kind of on the performance more from a battery side, but the application side is hugely critical as well to ensure consistent and high quality surface coverage. You can run into a number of issues when doing this. So we really marry kind of the material properties for that cell side performance, but also on the application side to ensure that based on Analog's pattern designs, you see a couple there to the right, that whoever the customer may be is using, our material sort of rheological profile is suitable to be able to high speed coat. And we don't want the material to be the limitation in the application process. We always want that to be the engineering of the equipment. So a couple of future trends where I see this going, lower coating thicknesses were constantly being pushed lower and lower. These conductive coatings are not active inside of cells, so there's a really push to limit that thickness and also increase the application speeds just from an efficiency and cost standpoint. If you kind of dive into literature on this, you'll see some enhanced functionality. I do anticipate some future developments of these materials kind of becoming more multifunctional to aid in areas, whether that be battery safety, or I just saw a paper recently on battery recycling, helping to kind of dismantle electrodes. Building in a functionality in that thin layer can help from that standpoint. And then lastly, some advanced architectures, whether that's via manufacturing process or all solid state. The work around conductive coatings kind of continues to aid and push some of the boundaries in the cell innovation in that regard. I'll just actually skip this. We're getting close to the time. We've been doing this for a long time in different energy storage devices. And Henkel as a whole has a variety of different things to support the automotive EV industry and the battery industry. I touched on one today. You can see a handful of others here as well. So lastly, summary, conclusion, and key takeaways. If you learned anything or took anything away from the last 30 minutes, my four main things is not all conductive coatings are created equal. There's a real benefit from understanding the relationship between these materials and how you're manufacturing electrodes. The second point kind of goes with that, understanding the use cases, kind of where it makes the most sense to use it, whether it's a technology enabler or it's just improving connectivity adhesion for low, high voltage cathodes. That third point, that's a key point. If you find yourself in a position where you're trying to do this, please reach out. Our materials will make life much easier when you try to get freestanding films laminated to current collectors. And my last point, we do have proven technology capabilities to support. Always looking to try new things as the battery community continues high-level innovation. We're always happy to support. We do have that Center of Excellence for Functional Coatings in Michigan and support globally with the tools for rapid innovation. So I thank you very much for those that joined and for your attention. I did say I had time beyond 1 o'clock. I'm happy to take any questions now, or if you want to follow up and have more lengthy conversations in the future, my email is firstname.lastname@henkel.com. You can also find me on LinkedIn and reach out to me there.